Hi, this is Paul from Foresight Tech. In this video, we are going to deal with the mean value theorem, which allows us to obtain information about a function just from the derivatives. Let's see the outline. First, I will introduce Rolle's theorem as a foundation. Next, I will introduce the mean value theorem and give a proof as well. Then I will introduce two important results based on the mean value theorem. Last, we will practice 3 questions together about how to use the mean value theorem to solve application problems. Let's see the material. Here is Rolle's theorem, which is the foundation for the mean value theorem. Okay, and Rolle's theorem states if a function f satisfies these conditions, then there is a number c between a and b, such that the derivative at c equals 0. Or you can say the tangent is horizontal, right? Or c is a critical number. Okay, so now let me highlight the condition first. Okay, so the first condition you can see is f is continuous on the closed interval ab. The second is the function differentiable on the open interval ab, because the endpoints we never talk about differentiable, right? And then we look at the third, which is the most important, is the value of the function at the endpoints are the same, right? Okay, so these are the 3 conditions. We have to prove the Rolle theorem, which is not difficult. Can you see we have only 3 cases, and the first case is the function is constant. The second case, the function can goes up from the endpoint, the value of the endpoint. The third case is the function can goes down. Okay, so let's go to the first and imagine if the function is constant between a and b, can we find a number c so that the derivative equals 0? Yeah, definitely, right? Why? Because any number between a and b, the derivative equals 0. This is the result we already used. Now the second case, okay, and if the function goes up, okay, so let's look at the condition. F is continuous on closed interval ab, and by extreme value theorem first, and we have a number c, so the function can reach to the absolute maximum value, right? And then by Fermat's theorem, and we know this number c is the critical number, which means the derivative equals 0. See, it's super easy to get the results. And the same for the third case. And if the function can goes down, okay, first by extreme value we have a number c, the function reaches to the minimum, right? And then by the Fermat's theorem, at this number c, the derivative equals 0, horizontal tangent line. And this is the proof. Now let's go into the mean value theorem. Here is the mean value theorem, and we call the Lagrange's mean value theorem because Lagrange proposed its mean value theorem. Who is Lagrange? Lagrange was an Italian mathematician, right, who proposed the prime notation we knew before. Okay, so the mean value theorem states if a function f follow or satisfy these 2 conditions. Let me highlight these 2 conditions, and you also can compare this condition to Rolle's theorem. Okay, so the first condition is continuous on closed interval ab, which is the same as Rolle's theorem. The second is differentiable on the open interval ab, still the same. Can you see? We do not have the third condition, which means fa equals fb, right? This time we do not have. And then we have a number c between a b, such that, okay, the difference of the value between a and b equals the derivative times b minus a. What does this equation mean? This equation, you know, the left is the delta y, right? So the right side is the derivative times delta x. Okay, do you remember the linear approximation we learned before? Delta y can be approximated by dy, which is the differential. Okay, so dy here is at a. If ab is very close, here is a, and there's an approximation. And the mean value theorem gives us the exact equal. Okay, you know the difference. The second, so the most meaningful one, can you see the left side on this equation? It just tells us the information about the function, right? However, the right side, we only need to use the information of the derivative. Okay, that's why at the beginning say mean value theorem allows us to find the information about the function from the derivative. Okay, so that's why. And let me change a little bit of this equation. So I will give you a geometric meaning for what is the mean value theorem. So how to do? Let me divide both sides by b minus a. So we don't have b minus a on the right, and the left side goes to fb minus fa over b minus a. Right? The right side goes to the derivative at the number c. What does this mean? This time we can see a meaning. So the left delta y over delta x is what? Is the average rate of change over AB, right? The right is what? Is the instantaneous rate of change at the number c, which means the derivative at c. Okay, if we use the velocity in physics to explain, that's much easier. So the left side is just the average velocity, and the right side is instantaneous velocity, which means no matter how you move, okay, and we can find at time c, the velocity at that time equals the average velocity. Okay, I hope that makes sense, right? And if we see the geometry, okay, it's very easy to get a proof, but it's not exactly, okay, it's a sense of proof. Can we see what is the average rate of change? If the function looks like this, we link these two time points AB, we get the slope of the secant not AB is the left, average rate of change. And the instantaneous rate of change, which means we need to find a point on the graph. You draw the tangent line, the slope should be equals each other. The slope of the tangent line equals the slope of the secant line AB. Can we do this? Which means parallel, right? Easy to do. You just shift this, AB goes up, and then you find the last point, which is the point that you need. Okay, so if you look at the right point, the right graph, we have this time, if we shift up, we find one point, or if you shift down, you find another point. Okay, and the theorem tells us at least exists one point, okay, like the first one. And this is a geometric. It's not exact proof. Now, let me give you a edge break proof. To prove the mean value theorem, we need the Rolle's theorem. However, the last condition does not satisfy for Rolle's theorem because f has different value on both endpoints. Okay, and so all we need to do is just modify the function, or we're going to construct a new function so that the new functions satisfy the last condition, which means the new function has the same value on both sides. Where is that modification? See, from this graph is here, hx. Hx is the distance between the original function and the straight line or the linear function. Okay, and if we shift this point to the left a, can you see the distance is 0? So h at a is 0. If we shift this to the right, h at b also equals 0. Therefore, h has the same value on both endpoints, right? So we can use the Rolle's theorem. See, that's the biggest trick. Now, let me go to find what is hx. Of course, from the graph you see hx equals the total height, which is f, minus the bottom. So the bottom belongs to the non-equation, right? The linear function. Easy to find the non-equation. Why? because we have the point, we have the slope, so we can use the point slope form to find the line equation. Let me write here is just this. So what is the line equation? The line AB. I use the left point A, which is y minus y0 is f at A, right? Equals the slope times x minus x0 is x minus a. And then add the fa per side, so we get f equals f a plus m times m x minus a. And what is m? The slope. Okay, so the slope, of course, you know this is the average rate of change, okay, which is this fraction. Delta y, okay, we use fb minus fa. Delta x, which is b minus a. Can you see? And this function exactly is the function I wrote here, okay, on the graph. Okay, so now we have h. So h equals f minus the line equation, right? And you also know h at a equals h at b, both equal 0. So by Rolle's theorem, we have a number between a, b, so that the derivative equals 0, right? Now from here, we're going to find what is the derivative of h at c. Okay, so I wrote it here. It's easy. The derivative of h, can you see? I directly put the c here, is f take a derivative, right? So f take a derivative at c minus fa take a derivative is 0, constant, right? And now is a linear term, take a derivative is the coefficient, which is fb minus fa over b minus a. You know this equals what? 0. Can you see? Is this the result? Okay, definitely. So f prime at c equals this coefficient. Can you see? And this is the instant velocity equals the average velocity, right? That's what the mean value theorem means. Okay, so why we call it the mean value theorem? Because this is the mean value, right? Because this is the average rate of change. Okay, so that's the proof. Okay, so we have the proof. And now let me introduce another two results directly derived from the mean value theorem. Here are the two results. Both are useful. The first theorem, okay, give us, and if we have a function f, and if the derivative equals 0 for all the x, then f is constant. Which means what? Which means if we want to see a function is a constant function, all we need to do is look at the derivative should be always equal 0. And look at it's obvious, right? Okay, and how to prove? And I'm going to show you we can use the mean value theorem easily. Okay, so let me draw a graph for you. The basic idea is this. And suppose we have this x and y, and if the function is a constant, how do you say this is a constant function? Okay, all we need to see if I pick any point x1, like any other point x2 on the domain. Okay, so f at x1 should be this, should be always equals this height, right? Okay, and if we can prove this, and that's this theorem. Okay, so I'm going to see what the difference between the y value. Okay, so fx1 minus fx2, I cannot see the difference. Why? Because the mean value theorem gives us, and we can find a point C, you know, like this. If we can find a point C, okay, so between x1 and x2, like this, okay, and take derivative, right, times dx delta x, which is x1 minus x2. See, this is the mean value theorem. Delta y equals f prime times delta x. And the derivative always equals 0. Can you see? That's equals 0. Which means what? Okay, all the y value keep the same. Is this a proof? Yes. Okay, definitely. Now, and we have another result. Okay, the corollary one. Okay, directly from the theorem one. Okay, and this result is this. Suppose now we have two functions. Okay, and if the derivative of the two function always the same, and then f minus g, which is the difference between the two functions, is a constant. Let me draw a constant. For example, if f minus g equals 1, what does that mean? That means f equals g plus 1. G plus 1 is shift up, right? Which means what? F and g is just a kind of shift up or down relationship. Okay, if I draw a graph, you can see it's just like this. Suppose we have this x, y. Okay, so if f is at here, for example, if this is f, where is g? Probably shift up or shift down. Okay, like this. This is g. Okay, it's parallel everywhere. Okay, let me going to prove how to prove this. Of course, we can directly use theorem 1. Why? The difference between the two functions. So this is a function. We're going to see if a function is constant. All we need to see is the derivative of the function equals 0. Okay, so we're going to find the derivative of this function, which is f minus g. This is a function, right? And they're going to take a derivative equals what? Equals f prime minus g prime. Okay, we have the differentiation rule, right? And what do we get? We get 0 because the condition gives us the derivative always equals 0. Is this a proof? No, by the theorem 1, of course, because the derivative of the function equals 0, so the function is constant, right? Okay, so this is the two results. And the one comment for these two results, you can see, okay, both the condition is the derivative. From the derivative information, we can find the information for the function, right? So this is important. Now, let's go into practice how to apply this mean value theorem to solve a problem. Here is the first question, and we have to show or to prove, and this equation has at most one row in the interval -2 to 2. Okay, so we are going to do this. We're going to use the Rolle's theorem, and we use a method we call the argue by contradiction to prove. Of course, you know Rolle's theorem is just a special case of mean value theorem, right? So this is just a kind of application. What is argue by contradiction? Let me highlight this. And probably you are not familiar about this method. Let me introduce a little. If we want to prove something, okay, first we set up a opposite hypothesis, okay, and then we do reasoning. If we find a contradiction, we go back to say the hypothesis is wrong. That method we call argue by contradiction. So for our question, we are going to set up the hypothesis which is opposite to what? To here. Okay, so we need to prove they are at most one row, which means we have to prove there are no two rows, right? No two rows. Okay, so the hypothesis opposite to this is there are two rows. Okay, so let me write it down. We're going to set up the hypothesis is this. We're going to wait. I pick this. We're going to set up the hypothesis, which is I say suppose there are two, right, rows in -2 to 2. See, this is the opposite hypothesis, and then now we're going to reason it. And by using the Rolle's theorem, I will find a contradiction. So I'll go back to see this hypothesis is wrong, which is the proof. Okay. And now what do we do? I have to set up the function. Okay, is this? Let me set up fx equals x raised to the third power minus 15x plus c. which means we're going to set up the function is the left side on the equation. And then what do we have? Because we already set up the hypothesis, there are two rows, right? And the two rows, which means 2, 0. Then we have this f at a. So what is a? Let me write down here. Two rows, one is a, another is b. Okay. So we have this, and the fa equals 0, and the fb equals 0, right? Which means fa equals fb equals 0. Now, see, and this function just follow all the conditions of Rolle's theorem. Okay, continuous, differentiable, and has the same value on both sides, on both endpoints, right? And then we can do this by Rolle's theorem. So we say, by Rolle's theorem, what do we have? Okay. By Rolle's theorem, okay, we can find a number between a, b. This number is c. We cannot use c because we have a c here. Let me use c0. Is okay. We can find a number between c0 between a, b. The derivative at that equals 0, right? Okay, so this is the Rolle's theorem. And let me write a little bit more. C0 is a number between a, b. Therefore, is in -2 to 2, right? Because what? Because a, b is between -2 to 2. And now, what kind of contradiction I can make? I can just, let me highlight here. We have this equation. Okay, this equation is not difficult to solve. I'm going to solve this equation. See what I get. I will get something contradiction. Is this, and what is the derivative? Let me going to see the derivative is, because this is a polynomial, easy to find, is 3x second power, which is c0 the second power, minus 15. Can you see this? Equals 0. That's the equation, right? What's the solution I can find? Of course, c0 square should be equals 5. Therefore, c0 should be equals either positive or negative square root of 5. Okay, what is square root of 5? Square root of 5 is more than 2, more than square root of 4. Okay, so what? So now I find that this c0 is not in -2 to 2. See, I highlighted in the red. This is contradiction. Contradicted with this. Okay, because we say c0 is in -2 to 2. But now we get the c0 is not in -2 to 2. What does this mean? This means contradict. Let me write it down here. Is a contradict. Okay. See. Okay. It's great. So now we get a contradiction. Therefore, what we can do? We can go back to check our hypothesis. This is a hypothesis which means wrong. That's wrong means what? Okay. Means there are no two rows, right? So let me write down. So there are no two rows. Okay. In -2 to 2. Is this the proof? Yes. Why? Because there are no two rows, which means we have only at the most one row, right? Now is already the proof. This is the proof. Let me go to see another questions. We're going to practice together. Here is the second question. And suppose we have a function at y is 10, and we know the derivative information, and how small can f4 possibly be? See, what does this question mean? Questions give you some condition about the derivative. Ask you to infer something for the function. Do you know? I think you remember at the beginning we said this is just the mean value theorem can do for us, right? Okay, so we're going to use the mean value theorem on the interval is 1 to 4 because the condition give us is from 1 to 4, and the condition should satisfied. Why? Because the derivative exists, therefore is continuous and differentiable, right? And how to describe the mean value? Of course, they ask us f4. We're going to directly write this f4 first. We're going to find f4. How to find f4? The mean value theorem is stay in this f4 minus f1, which is delta y, right? Delta y equals f prime at a number c between 1 and 4 times delta x, right? What is delta x? Delta x is 4 minus 1, and the c, of course, is between 1 to 4, right? This is the mean value theorem. And now from here, so we can solve for what we need. We need the f4, right? So I'm going to solve f4. I plus f1 both sides. Therefore, I get f4 equals f1, right, plus f prime at c times 3. Okay, so let me see, times 3. Now almost. I will write what is f1. f1 is 10, so it's 10 plus 3. I switch a little bit order, times f prime at c. Okay, so how about this? Let me highlight. How about this? It's okay. So this one we already have, and check the condition. So f prime always greater than or equal to 2. Therefore, what do we get? We will get this one is greater than or equal to 10 plus 3 times, let me use this color, is 2, right? Okay, so this is almost. Let me calculate it. The answer is 16, which means we get this f4 greater than or equals 16. So what is the answer? What is the possible smallest number for f4? Is 16, right? Therefore, okay, so 16 is the answer. Okay, looks easy to get, right? All you need is just follow the mean value theorem. This is the major application. Now we have another application. Here is the last question, and also another important application for the mean value theorem. Can you see? We have to prove this identity for all the x between 0 to 1. Okay, we can do in this way, which means the left side minus the right side equals 0. We have to prove this, right? If we set up the function is the left minus the right, which means the function equals 0 equals a constant number. Do you remember theory 1? So how to verify a function equals a constant number? All we need is to find that the derivative equals 0, right? So these type of questions is super easy. All you need to do is just do calculation. Okay, find that the derivative equals 0. Let me write down. Okay, so what is the function? Of course, let me write a little bit. So let me set up the function. Let me define fx is just the left side minus the right side, right? So it's 2 inverse sine minus inverse cosine at 1 minus 2x squared. Okay, and then we're going to find the derivative. We should find the derivative equals 0. Is the derivative equals 0? What is the derivative? Okay, and the first term is 2 times the derivative of inverse sine. You remember is what? Is 1 over square root of 1 minus x squared. This is the formula. And then minus, what is this derivative? Can you see? Cosine at u, this is a composite function. We have to use a chain rule. Okay, cosine u is the outer function, and the inner function u is a polynomial. Of course, you know how to do, right? Let me write it down. So I have to times the out, which is that's the formula. Okay, so negative 1 over square root 1 minus u square, okay, which is 1 minus is u is 1 minus 2, right? 1 minus 2x square, put the square. Can you see? And this is what we find is just the derivative of the out times the derivative of the inner. The inner is a polynomial, which is easy, right? Is negative 4x. Okay, this is the chain rule. Now all we need to do is just simplify. Little bit of calculation, you have to pay attention, but the method is super easy, not difficult. So the first I get a 2 over square root of 1 minus x square, right? And then now the second term I can simplify a little. See, negative negative goes to positive, and see here is still negative, so still minus. Still minus. Now is a fraction. Okay, the numerator is 4x, of course. What is the denominator? I will going to simplify the denominator a little bit longer. And the denominator inside the square root is 1. 1 is 1 square. 1 square minus this square. This which means that the difference of squares, right, is the sum times the difference. I will going to use that formula. So easy to get what is the sum. 1 plus 1 minus that, which is 2 minus, okay. So it is 2 minus 2 times x square. This is the sum times the difference. The difference 1 minus 1, 0, okay. And then minus negative is plus. So we have 2x square. Let me see, is 2x square. Okay, so now much simple. Of course, we can continue to simplify. The first is still copy 1 minus x square, and then minus. Okay, so what kind of simplification we can do? Can you see the denominator 2, we factor out the 2 times this 2 factored out, we have how many? We have 2, right? 2 and 4 we can cancel 2, so the numerator we have 2x. And what is the denominator? We have a square root of 1 minus x square, and this x square we can factor out. Okay, we can put outside of the square root, because x between 0 to 1 is a positive value. Therefore, x squared take out is x. X we cancel. Imagine what do we get. Now, we get exactly the same with the first term, which is 2 over square root of 1 minus x squared. What's this? This equals 0. That's what we just imagine, right? So we expected this. So, and what do we have? By the theorem 1, okay, so we have f x should be constant, okay, should be equal to c, like, you know, c is like a constant number, okay, and for all the x between 0 to 1. Is this the proof? Almost, okay, and what's the identity? The identity we should prove f equals 0. Now we get f equals a constant. All we need is to find the c equals 0, right? Let me go and find the c equals 0. What do we find the c equals 0? Because this constant function is equal to which constant number? We just plug in any number is good, okay? I will going to do this now to determine what is the constant number c, right? To determine the constant number c, easy to put. Well, I just put x equals a specific number. Which number is easy? Let me see. F at f is here. If you are familiar with the inverse trig functions, you can put like 1/2. Okay, it's good enough. 1/2 we can find exactly the inverse value. Okay, let me put the easiest 1/2. I will put the x equals 1/2 into the function, right? And then what do we get? We will find C. Okay, now it's just a do calculation. C should be equal to f add 1/2, right? What is 1/2 the functions? If we go back to the function, see, it's 2 times the inverse sine minus cosine. Okay, so remember that. Let me put, which is 2 times the inverse sine add x, which is 1/2, minus the inverse cosine, parenthesis. Okay, let me go back. When x equals 1/2, see, when x equals 1/2, x squared is 1/4, times 2 is 1/2, 1 minus 1/2 is 1/2. Okay, so here, that's why I said I pick x equals 1/2. So this is still 1/2, almost. If you go back to the inverse function, this means angle. The angle is what? Is 30 degrees, because sine 30 degrees equals 1/2, right? So that we get 2 times 30 degrees, which is pi over 6. What is inverse cosine at 1/2? This time is 60 degrees. That's pi over 3. Okay, and do calculation. What do we get? We get 0. So that's what we need. So what do we have? So fx equals c, right? C is 0, so fx equals 0. Okay, and for all the x between 0 to 1. Okay, and if we go back a little bit, this means what? Fx equals 0, which means, can you see? Fx equals 0, which means the left side is equal to the right side. Okay, let me write it down. All we need, that's the final. Okay, that means the left side 2 times the inverse sine at x should be equals inverse cosine at 1 minus 2x squared. See, that's the proof for this identity. And we learned a lot of identity in trigonometry. Okay, if you use this method, you can prove most of the identity you learned before. And that's all. Thank you. I hope you enjoy learning on this topic. If you have any question, please leave your comment. If you like this video, please give me a thumbs up. Thank you for your support. Please don't forget, you are very welcome to subscribe to my channel for more videos. In the next video, let's see. We are going to deal with the shape of a function using derivatives. Hope to see you there. Thank you. Have a nice day. Bye.